It's a pleasure to have Jordan Cotler, who has just joined Harvard. He's going to talk to us about Euclidean wormholes and gravitational constraint instantons. So yeah, thank you, Jordan.
Great, thanks so much for having me. So everyone, you can see the screen, so yeah? Okay, so great. So thanks again for having me. And of course, as yeah, feel free at any point to interrupt with questions or election results or anything like that. And I'm going to tell you about 3 papers from this year, all in collaboration with Christian Jensen. And the talk is about Euclidean wormholes and gravitational constraint instantons. And I'll have to tell you a bit about what exactly are gravitational constraint instantons. So before I begin, let me tell you the punchlines of the talk, which roughly correspond to summaries of these 3 papers. So we'll get to these in turn, but one of the main punchlines is that there's a vast collection of new non-perturbative effects in the gravitational path integral in greater than or equal to 3 space-time dimensions and for all values of the cosmological constant, specifically anti-de Sitter, de Sitter, and flat space. So these will correspond to Euclidean wormholes, interesting cosmologies, and also give hints of ensemble gravity, or what has recently been called ensemble gravity, in higher dimensions, namely higher than 1 + 1 dimensions. And as a particular example of these phenomena, we will study ADS3 gravity, which will show in codes a generalization of random matrix theory. We'll show that certain non-perturbative effects in ADS3 gravity encode random matrix theory-like statistics, and will provide a compelling and quantitative calculation which provides evidence for a putative ADS3 ensemble duality. And one other thing to say, although depending on how much time we have, I may not get to it, the ensemble gravity amplitudes can be accessed by a generalization of the conformal bootstrap. And in the case of this, these ADS3 non-perturbative effects, we'll find that we can actually exactly compute the ADS3 wormhole amplitudes using bootstrap, a generalization of bootstrap technology. So we'll get to these in turn, but let's start from the beginning. And suppose that we're given a path integral. Then the first thing to do is to find a classical solutions of the action. So as an example, suppose that we have the path integral for a scalar field, and we have some Euclidean action. And what we do is we look at the equations of motion by looking at the variation of the action. And for each classical solution, we must then work to understand its physical meaning and study the quantum fluctuations around it. So this is the usual modus operandi of path integrals. You find the saddle points and you consider fluctuations around them, and you study what you want to study. So I should say for the rest of the talk, I will set h bar equal to 1, and similarly with the speed of light, but I will keep Newton's constant for our discussion of gravity. So one way that we can think about a saddle is as a point at the bottom of a bowl. It's actually, in this case, a particular kind of saddle, a stable saddle. Namely, it's a point or configuration which is stationary in all directions. But what we're going to be concerned with are not saddles per se, but objects called constrained saddles. And one way of thinking about a constrained saddle is like this alpine slide, where you see these people sliding down. And a constrained saddle is a configuration. So let's look at the location of this person in their sled, in which you are stationary in all but finitely many directions. So in this particular case, this person is stationary to the left and to the right, but they're not stationary in the up-down direction because there's a slope. They're going down the hill. So in general, a constrained saddle is a configuration which is stationary in all but finitely many directions. Now in 2 dimensions, that's less interesting. It just means that you're stationary in one direction, but not stationary in the other direction. But in infinite dimensions, as relevant for path integrals, such as when we integrate over field configurations or spaces of metrics for gravity, we're going to be interested in configurations which are stationary in every direction, in all of the infinitely many dimensions, except for one. And that is going to be far more, anyway, it's far more special than this phenomena occurring in lower dimensions. So we'll talk a bit more about these in concrete examples, but I want to argue to you that constrained saddles are the next best thing to saddles. And by definition, of course, they are off-shell configurations, but they've been shown to capture interesting physics in some scalar field theories and gauge theories, and more recently in Joukiffe-Teitelbaum gravity. So what we're going to do in the first part of the talk is we're going to find moduli spaces of constrained saddles in Einstein gravity in all dimensions, all space-time dimensions, and for all values of the cosmological constant. And then we will talk about what is their physical interpretation. And this will be related to Euclidean wormholes and to ensemble aspects of gravity in higher dimensions, potentially. So good, so I said these correspond to Euclidean wormholes as well as cosmological spacetimes. And we're also going to initiate a stability analysis of these constrained instantons, and we'll be able to show that some of them are stable. So as I said, we'll investigate the physics which underlies these solutions. And as an example, in the context of ADS3, we'll show that some of the constrained saddles encode the energy level statistics of black hole microstates, specifically BTZ black holes. So here's the outline of the talk. I'm first going to tell you about constrained saddles in particular, in general, and then in particular in Einstein gravity. Then we'll talk about a zoology of constrained saddles, and namely a bunch of different ones that we found and their various properties. And then as a case study, we will talk about constrained saddles in the context of ADS3 gravity, where we will study, as I mentioned, black hole microstates and the connection to random matrix theory. And finally, we will conclude with a discussion. So let's begin with constrained saddles in Einstein gravity. So what are constrained saddles? So let's begin with a historical example due to Affleck. So let's consider 4D scalar phi-4 theory with a wrong sign quartic term. So in the classical massless model, so if we set the mass equal to 0, then there are instantons with position modulus x0 and size modulus rho. So here is an example of the profile of such an instanton. We see that the size of the instanton is dictated by rho and the position is dictated by x0. So, however, if we turn on the mass in the theory, then we find that there are actually no such solutions. These solutions go away as soon as we turn on the mass in the theory. So, however, on physical grounds, you might expect that the instantons, which are much smaller than the mass scale, namely when rho is much smaller than m, should persist. That in a certain sense, if these instantons are small enough, you would imagine that they don't see the mass scale and it looks effectively like a massless theory. But nonetheless, there are no solutions to the massive theory, even though you might expect them to still exist in this regime where rho is much smaller than m. So what happens, or there's some puzzle here. How does this happen? Where do these instantons go? And this is the question that Affleck addressed in his paper. And I'll tell you how this works. So here's the basic idea of Affleck. He says, well, let's examine configurations at fixed size rho, at fixed size of these instantons. So for non-zero mass, these configurations are not classical solutions, as I said, but they still contribute to the path integral. So here's what we're going to do. So let's consider, here is the path integral for our theory. And what Affleck does is he introduces a constraint in the following way. Let's consider a constraint, so we have a constraint functional C of phi, which is going to take a phi configuration, and it's basically going to compute some function of rho. Basically, it is a functional of phi which extracts the size modulus, and we're going to have a delta function constraint which sets effectively the size modulus equal to zeta, where zeta is some fixing parameter. But we're then going to integrate over zeta. So what we're doing is we're introducing a delta function constraint, but we're rendering it innocuous by integrating over zeta. So we say that we constrain this to be equal to zeta, but we integrate over all zeta. So we're effectively inserting the identity. But now what we're going to do is or what Affleck does is that he takes the delta function and we exponentiate it, basically using the Fourier representation where lambda goes along pure imaginary contour. So this is just the same integral that I showed you before. And in fact, it's equivalent to the original integral because we put in a delta function that we integrated out over the constraint, and then we just rewrote the delta function in terms of a Fourier type representation. But now is where things start to get a little interesting. So now what we do is that we vary the phi field, and we vary the lambda field, but we keep the zeta field fixed. So usually what we would do if we wanted to compute a saddle point approximation is we would vary all of the fields. We would vary phi, lambda, and zeta. But now we're going to just vary phi and lambda, which gives us this equation when we vary phi, and this equation when we vary lambda, the constraint equation. And this is all for fixed values of zeta. So what we do is that we solve these equations as a function of zeta. So we get solutions to these equations that are as a function of zeta. And we then do a one loop approximation in the phi and lambda degrees of freedom. And then we completely integrate over the residual zeta degrees of freedom. So in other words, we are doing a saddle point in phi and lambda, but completely doing the path integral in the zeta direction. And there's a question about why is this justified? And I'll say more about that shortly. But does this make sense?
Can I ask a question?
Oh, yes, of course.
I'm just curious how unique this prescription is. Like if you use different variables, would it, and then you constrain those different variables instead, would it give you the same answer?
Yeah, so the way to think about it, as we'll see shortly, is that what you're looking for, okay, so back in this language where you have these configurations in field space, which are, so you have this, it's like a valley. You have this valley direction that you're integrating along. That's like the zeta direction. And you would like the remaining degrees of, the remaining directions to be stable in terms of their quadratic fluctuations. But the key point is that you choose a constraint. You would like to choose a constraint which is, how do I say, orthogonal to the valley. So in other words, you want to constrain it on slices in which you are stable in the directions that are orthogonal to the zeta direction. Does that make sense?
Yeah, thanks.
Sure. Great. So,
Jordan,
yes.
I just had a quick question. So this general framework that you're describing is a specific example of this how people compute the like saddle point for a fixed area eigenstates to like get the leading order entropy. Would that be like an example of this?
Yeah, so I believe so. I believe that is an example, although I haven't thought about, yeah, I believe that's right, but I haven't worked through the details of matching it with this exactly, but I think that's true.
Okay, but I guess more generally, conceptually, like is the idea that, so you insert this identity operator, which is like summing over all these different zetas, but in like there's a way where you don't have to actually do the entire sum over zeta by doing a saddle point in lambda. Like,
sorry, you do have to integrate over all zeta, but you do a saddle point in lambda and phi.
So what is the saddle point in lambda get you? Like what is it that it allows you to, like, well, yeah, what's the edge that it gets you?
Yeah, so, okay, so maybe let me say it this way. So it's actually this particular point on the slide that I was gonna say, which I think, but if it doesn't address your question, please feel free to say so. But also related to what Raphael was asking, the precise constraint is not important in a certain sense. I view it like the way that we are going to view it. Okay, it's just a tool for basically finding these non-perturbative configurations which can be path integrated using standard methods. In other words, the constraint is just like a tool for us to find these valleys, which we are then going to integrate in the orthogonal directions. So this constraint trick is like, if you do it correctly, is a way to access these valleys and to find them. But if you have an inspired guess and you can find and you can show that they exist, or that you can find, if you didn't know anything about the constraints and you just knew which configurations to look at, you would not have to go through the procedure I just told you. It just so happens that in various examples, it's easier to reason by choosing an inspired constraint. But once you have that, then you can proceed as if you just knew what you were doing all along. Does that sort of help? So the details of, so this is slightly maybe deceptively phrased. The constraint does matter in the sense that you want to be orthogonal to the valley, but you want, that the fluctuation should be positive in directions that are orthogonal to the valley, but nonetheless, but once you kind of know what you're doing, then you can just use sort of standard methods to value the path integral. Just saddle in those directions, integrate in the valley direction. Does that sort of address your? Okay.
Yeah, that makes sense. Thanks.
Great. So, okay, so the configurations are near saddles. As I said, they're stationary in all but one direction in field space, and they provide important non-perturbative contributions to the QFT path integral. And there's some other examples in gauge theory that are somewhat famous, but I won't go into those here because we're going to be mostly interested in gravity. So let me give a finite dimensional example just to sort of orient us before we go into the infinite dimensional setting. Here's
I'm so sorry, but just
yes.
Going back to this instanton that you were discussing in the beginning.
Yes.
So normally, if we don't have exactly a stationary point, then we would expect that the phases will cancel and I don't get much of a contribution. It's the point that as I take the mass to zero, the phase sort of becomes stationary and you get the usual argument back for why the saddle point is important?
I mean, so how do I say? So when you're doing stationary phase, you would like, I suppose, you would like to have a slow direction. Like you would like the valley to be slower, how do I say, slowly sloped or something like that?
Yeah.
But in the Euclidean setting, it's less clear that that's a problem. I mean, just because, how do I say, there's no I. So it sort of depends. There's various things that can go wrong in the Euclidean case, but you don't necessarily need to, you don't necessarily need to have it be slow. I mean, the problem is when you say slow, you mean with respect to slow relative to something else, maybe but I'm not sure if that answered your question, but the short answer is that if you're doing the Euclidean calculation, it's a slightly different consideration.
Why? One question. Why are you not saying that to going to Euclidean, the slowness of the phase is not like just the slowness of damping? That's the usual thing, right? It's just minus e to the minus a small number. It doesn't damp.
Sure. I mean, so let's think about it this way: is that so maybe let me say it in a slightly different way. We're going to be considering situations in gravity, such as, one example we'll consider is ADS with two asymptotic regions, and we're going to look for wormhole solutions, in which there are no classical saddles, which describe there are no classical solutions to the Einstein field equations, which give these kinds of Euclidean wormholes, or which satisfy these boundary conditions. And one thing you could do is you could, you could say, how do we evaluate the path integral in the absence of a classical solution? And what you might say is that, well, okay, if I were to find these valleys, what you're saying is, well, what we should do is we should really extremise along the valley. Okay. In other words, we should find the place in the valley which gives the dominant contribution. And if it varies slowly, then maybe a better approximation is to integrate along the whole valley or something like that. Yeah. But we're going to be in a regime in which, so maybe we get some, let's put it this way, it can't hurt us to integrate along the whole valley per se, although you might expect that the answer would be dominated by, the highest point in the valley or something like that.
Then it's fine.
Yeah. So to maybe even be precise, I'll give you an example of this phenomena right here, which is just like a 2D integral. And so here we're integrating over b and x, and let's say that n is some large parameter. So the saddle point equations, okay, so if we vary in, we just take the derivatives in b and x, we get this and this. I'll rewrite the second equation, I'll just rearrange it. So notice that this equation actually has no solutions for b greater than or equal to 0, because e to the b is strictly positive on the domain 0 to infinity, and likewise cosh on minus infinity to infinity is strictly positive. So this is an integral which you'd like to do a saddle point equation, you'd like to do a saddle point approximation to naively, but there simply are no saddle solutions. And so the idea is, let's throw away this equation. So let's fix b And let's consider a constrained saddle. So if we fix B and then we vary X, then we find that there's a line of constrained saddles at X equals 0. So the valley, so to speak, is basically the line X equals 0 as you vary B. And in the X direction, the fluctuations are stable, as you can see by just expanding cosh of X around X equals 0. So the kind of approximation we're going to consider is that so this is so we just expanded cosh of X around X equals 0. And then, there should be an e to the b here. But then we do the saddle point approximation in X, and then we compute the residual integral in B. And what was being asked before is you could say, well, should we do a saddle? I mean, okay, well, you say should we consider the B, which is the smallest value of B equals 0? And there are various reasons why, because of the presence of the boundary, that it's actually sensible to integrate along the entire valley. And okay, well, the right-hand side doesn't mean anything. It's just some special function which is equal to the left-hand side. But this can be shown, that this is actually a very excellent approximation for even modest values of n of the original integral that I showed you. So if you evaluate this, where we saddled an x, and you compare it to the original integral, it has the sort of small corrections that you would expect as if we had done a standard saddle point approximation. So here's the question, which is, are there constrained saddles in Einstein gravity? And so previously, as I alluded to before, people have found constrained saddles corresponding to Euclidean wormholes in 2D dilettante gravity. This was initiated by Saad-Shankar and Stanford, where they computed what's called the double trumpet, which is some two-sided configuration in nearly ADS2 Joukiffe-Heidelbein gravity, which tells you about random matrix theory statistics, because that theory is dual to a random matrix theory. But it's also, it's been shown in other examples of 2D dilettante gravity more generally, and these constrained saddles play an important role in that analysis, or that is how you do the analysis. But there's a popular view, I'm not sure it's necessarily, I mean, depends who you ask, that stable two-sided wormholes are an artifact of topological theories of gravity, or by really what I mean is low dimensional gravity, and may not exist in higher dimensions as stable solutions of the, they're not necessarily sensible. And there have been various proposals about how to have stable wormholes, axion wormholes, gravity coupled to Yang-Mills, but all of these have been shown to be unstable by various mechanisms, and these are ordinary saddles, these are not constrained saddles. So the status of wormholes and higher dimensional gravity that are stable is sort of a little murky. But the answer to this question that we asked of, are there constrained saddles in Einstein gravity, is yes, there are. And we are going to choose an inspired constraint, which was inspired by a recent paper by Douglas Stanford in 2D gravity, but also more broadly what Saad-Shankar and Stanford did. And so just to orient ourselves, let's draw a picture of a two-sided spacetime. Let's consider the ADS setting in which these are asymptotically ADS boundaries, and let the direction along the wormhole be rho, and we'll set rho equals 0 to be the position of the bottleneck. So this, this over here is going to be the rho goes to infinity, and this is the rho goes to minus infinity directions, just to set some coordinates. And we'll let the boundary, the metric on the conformal boundaries be gamma 1 and gamma 2 respectively. So there's two different ways that we can view the constrained saddle problem. One is non-covariant, but has a certain intuition to it that I'll tell you first. And there's a second way to think about it, which you may like better, which is actually fully covariant. But the way that looks most like what's been done in the JT context is, okay, so let's do some gauge fixing where we go to something like Gauss normal coordinates, where we set the g rho rho equal to 1, and we set the g rho I parts of the metric to be equal to 0. So xi are the non-rho directions. And the constraint that we want to impose is this constraint. And what it's doing is it's basically computing the length of the wormhole. It's computing the length, loosely speaking, from one side to the other. So so in other words, we want to solve these two-sided we want to solve Einstein gravity with 2 asymptotic boundaries, we're constraining the length of the connected geometry between them. And when you do this, this ends up being the modified set of equations of motion that you have to solve. It looks like the Einstein field equations on the left-hand side, but you get this this term on the right-hand side in the rho direction, which is due to the constraint. And so you want to basically solve this at fixed values of lambda, which is related to the size of the wormhole or the length of the wormhole. And we find many families of solutions to this. But this doesn't look very covariant, at least not manifestly, because we've chosen these, these kind of Gauss normal coordinates and such. But there is a different way of thinking about this, which is covariant, which is that let's consider, let the ADM energy on the 1 boundary be E1, and let the ADM boundary, so the ADM energy on the 2 boundary be E2. What we are doing is we are solving the Einstein field equations where we are fixing, so we are fixing the value at the boundaries of the ADM energies to be equal, and to be equal to some fixed value E. And that is equivalent to this other prescription that I told you. You get the same constraint saddles. And you might ask what happens if you were to fix E1 and E2 to be different from one another, and you don't find any solutions in that case. So you can think about these as solutions to the Einstein field equations, 2 boundaries, connected solutions with fixed and equal ADM energies at the boundaries. And then at the end of the calculation, so we compute things for fixed energy, and then we integrate over energies at the end, much like we were doing before. And indeed, the calculations done in JT gravity can also be cast in this form, and this was done so in this paper by Douglas recently.
I'm a little confused.
Configuration is time invariant.
I'm sorry?
Right? Time goes to minus time invariant configuration, right?
Not, so you're saying are you asking, does it have to be symmetric and rho goes to minus rho?
No. Oh, is it? Okay, sure. Okay, I got it. Forget about it. Yes, thanks.
Okay.
Can I ask something?
Yes, please.
Yeah, so I'm confused. Why are you calling this a constraint saddle, and why would you integrate over the energy? I mean, normally we could just specify normally we get to specify some boundary condition.
Sure. So suppose we specified the boundary condition of the ADM energy being on the left boundary and right boundaries being E, both being E. There are no, or how do I say? What I'm saying is that this is already carving out a valley in field space or in the space of metrics. And the residual, and you can find, there are saddles once you do this fixing. So this is different than the usual, I mean, this is different than, these spacetimes are asymptotically ADS at the 2 boundaries. That's a separate consideration. But we are additionally going to impose the values, the fixed values of the ADM energies at the boundaries. And so that is additional to the usual asymptotically ADS boundary conditions. So it's like, that's like the constraint. Did that address?
I guess what I'm confused about is that normally I would expect that if you had a constraint saddle, that there's some place where it doesn't satisfy the equations of motion.
Oh, well, how do I say? It doesn't. I mean, if you allow variations in the E direction, it won't.
Yeah,
I'm
but
saying,
I didn't think that the energy at infinity isn't really a dynamical variable. I mean,
how do I say? I mean, I think maybe a better picture, I mean, how do I say? This other picture might be more intuitive about the length of the wormhole, which, like, you can basically write one in terms of the other since they're related, is that it's like looking at configurations of fixed length. It just so happens that the length is related to the energy.
I mean, I'm kind of confused by the same thing, and the reason I at least that I'm confused based on what you just said is I thought the fixed length thing is what Saad, Schenker, and Stanford tried to consider, where you have 2 fixed length boundaries, and that
No, I mean the length
wouldn't
from
be
one
on
boundary
shell.
to the other.
Sorry?
I mean this length from gamma 1 to gamma 2.
Oh, I see. Well, okay, I guess what's confusing is if you integrate over all the different energies, it basically seems like you're asking whether there's something like a thermal field double kind of configuration, because it's kind of, you take a fixed energy state and then you're kind of integrating over all the different energies. So it looks sort of like a two-sided black hole. And I thought those aren't saddles. So I'm just a little confused which part of this is slightly off shell.
I mean, okay, so again, I think that the thing that might be tripping people up is that is writing it in terms of, I mean, how do I say it? There's a relation between the length and the energy, or well, so yeah, so maybe let me say it this way. It's that okay, so would you be happy if we talked about configurations of fixed length? Like length is something that you might be happier to fix as the constraint.
Yeah, I think I just think I'm just missing something very basic. So I apologize for that. But
no.
I would have thought like that. So you see the inner circle that you have. Yes. I would have thought the like constrained solution is one where you fix the length of that thing. Because in the absence of the constraint dynamically, the reason it's off shell is it wants to shrink to 0. So like somehow you want to put a constraint that forces it to be a fixed length or something. But I think my intuition is off and I'm just not sure why.
Oh, so what we're going to find is that that's going to be, we're going to find a moduli space of solutions which are partially parameterized by that length or by the bottleneck. That's what you're saying?
Yeah, the bottleneck length, yeah.
Yeah. So
okay.
There is
yeah. So maybe related. So that's why I think what I asked is that suppose you fix the energy in two-sided usual black hole,
yes.
And then you still, with a fixed energy, you can change the length of the wormhole by just doing a time evolution in a same direction in the left and right boundary. So it's not one-to-one correspondence, but it's one-to-one correspondence if you require a solution to be time symmetric, namely the thermal field double. And then that may be steep direction. And that was my question, is that the steep direction is this time evolution, not in a symmetric direction, but it's the same direction in left and right. And that pick up a thermodynamic thing under the constraint. Then of course, constraining the length is equivalent with the constraint on the energy.
Okay.
And my question was that the right way to think? Yeah.
So perhaps I'll have to think okay, so maybe in real time, I didn't fully understand every detail of what you were saying, but but it sounded perhaps right. Sorry.
Because the interior volume becomes longer and longer, right? Even if you're fixing energy.
Sure. I mean, how do I say?
Oh, I think Yasunori is actually saying, or maybe asking the same thing I was asking, if I understand correctly. Just like in a dynamical situation, the wormhole is going to keep increasing in length, and then the interior will eventually just pinch off. But it's like what you're doing is you're forcing that length to be fixed, right? So that's like the constraint.
Sure. I mean, it's also Euclidean. We're also looking at Euclidean solutions for the moment, so there's no.
Yeah, that's true.
Yeah, that's why this understanding is not really one-to-one. Yeah, so it's like that's why I said forget about it. So it's not really, but it's maybe related. I don't know.
Sure, but I mean, we're literally going to do. But anyway, this is the thing that we're going to do, which is analogous to what, Saad Shankar and Stanford did.
Yeah, I don't want to hold it up too much. So I was just like, maybe could you just explain, if you second, why these were off shell in the context of SSS? Like, why is it that they don't solve the equations of motion in that case? Because I think that might help.
So there's a few different ways of thinking about it, but it's just that why are these? Oh, just because if you vary in the direction of the constraint, it's not stationary.
Yeah, so I get that. I was just wondering if there's like a physical picture for it, but maybe there just isn't because it's Euclidean and I'm asking for too much.
No, I mean, okay, I'm not sure exactly. Yeah, let me
Like-
think. Okay.
Okay. Yeah. Go for it. I can always ask at the end. No worries.
Yeah, let me maybe think about that, and or let me get back. I'll have to think about what kind of answer would be the one you would like. But maybe let's get back to this a little later. Is that all right?
Yeah, that sounds good for sure.
Cool. So, okay. So let's just talk about some solutions. And so we find many moduli spaces of explicit solutions, which are grouped as follows. So it's sort of like a choose your own adventure. You get to choose value of the cosmological constant, the boundary topology, and the behavior at r equals 0, which is where the bottleneck is. And let's look at ADS with torus boundaries and wormhole type behavior at rho equals 0. So this is what we should imagine for these ADS Euclidean wormholes. So let's begin with the case in which the two tori are equivalent, or namely they're identical. Here's an example of a constrained saddle, and this also includes twists, which are basically how do we say? It's relating the coordinates on one torus to the coordinates on the other torus. You can have a relative, the coordinates can change as you go from rho goes from -infinity to infinity. And the moduli, there's moduli of these solutions. This is sort of related to maybe what was being asked earlier, which is B, which is related to the size of the bottleneck, and also tau I, which are basically the amount of twist in each coordinate as you go from the one boundary to the other. So what you're supposed to, so I'm saying for each kind of, how do I say, fixed value of the constraint, you have to integrate over these moduli. This is also what is done in the JT case. The module, yeah, I mean, okay. So this solution, or this moduli space of solutions, these symmetric solutions, I call them symmetric. They're symmetric because the tori are identical. And actually a neighborhood around it is actually quadratically stable in pure gravity. And it's also true when we couple to a scalar field and a gauge field. So we did a stability analysis and we found that it's quadratically stable in the directions that are unconstrained. So that means that in other words, the valley has ridges which go upwards. So there's this valley direction and the other directions are stable. So these configurations are stable in the EFT approximation. And in fact, if you analytically continue these to Lorentzian signature, you actually get traversable wormholes. You can shoot a light ray or particle from one side and it'll end up on the other side. And a more elaborate example, you can ask, well, what if you change the conformal structures on the two tori? And so suppose that we have this be a d-1 torus cross a circle of circumference beta 1, and this one be a d-1 torus, a canonical d-1 torus cross a circle with circumference beta 2, then, okay, so here's an example of a more complicated family of constrained saddles. And you see that this reduces to the previous case for beta 1 equals beta 2 equals 1, just to give you a sense of what these things look like. And then I'll give one example, which will be important for later. In ADS3, I can actually write out for you the explicit solutions with arbitrary boundary tori, where they have arbitrary complex structures. And this is what those constrained saddles look like, where A and B are 2x2 non-degenerate commuting matrices. And we'll see later that these constrained saddles encode statistics of black hole microstates. These configurations are the analog of the double trumpet-like configurations in JT gravity that give what's called the spectral form factor in JT gravity.
Okay, now I think I understood the setup. I guess, but let me ask you. Like the first question is why? I mean, usually boundary condition is fixed. The boundary condition is energy. But I think you this as a model of the black hole. So that means it's coupled to external system, like what people are doing. Namely, boundary is glued to say flat space or something. You're imagining that. So this is a system. I mean, if it's an isolated system, yes, energy is preserved. No? But you imagine that this is a black hole. You can change the energy by radiating. And then you need to constrain because you have an E direction in a combined system.
That's possibly a possible interpretation, but I mean, how do I say? It's that, I mean, the thing which I usually specify when is a boundary, how do I say, is a boundary property of the metric. And the ADM energy also depends on the entire metric, not just what's happening at the boundary, even though it's a quantity which you can think of as living on the boundary. So
Oh, is it? Okay, yeah. Oh yeah, I think, okay. Okay, I think that also,
right.
Okay, I think yeah, I think that answers, yeah, probably, yeah.
Okay, so that sounds good.
Can I ask one question just for confirmation? So I think the solution, your constraint instanton configuration, you can also realize it as a solution with adding some like double trace deformation at the boundary.
Sorry, adding what?
Adding like the boundary double trace deformation and so on.
Double trace deformation?
Exactly.
I mean,
but that's a way to get the configuration, but
yeah, that's possible. Although,
but this is like a purely the gravity calculation.
Yeah, this is pure gravity. That's right.
It can contribute to the gravity passing integral.
Yes, that's right.
Yeah,
exactly.
I think that people is a bit confused that they can be realized through some as a solution of this system with some external coupling and so on.
Yeah, so I can say a bit more about, okay, so let me maybe comment on that for the moment, which is that, okay, so let me just run through a few facts that are relevant. So on the one hand, there are no classical solutions in the case of two asymptotically ADS regions which have a connected boundary, or sorry, a connected interior. There aren't any classical solutions with these boundary conditions, say two tori like this. So the claim is that the dominant contribution to the path integral is given by these constrained saddles. Now, if they're indeed stable, as they are in certain cases that we can compute, you might ask, well, what is their status? Okay, so this is maybe going a slightly different direction, but it'll relate to what you're saying in a moment. What is their status in ADS CFT in the context of the factorization problem? Are there additional things like, Ramon? I mean, are there additional things that we have to include to do a stability analysis? But so one tentative conclusion that you might say is that in the context of something like a ADS CFT where you have two asymptotic regions, but you have a Maldacena-Xi-like coupling, which creates this eternal traversable wormhole, that this is a context in which you might wonder if this matches on in an EFT sense to these constrained saddles. In other words, you could ask, how are these constrained saddles realized in string theory? And the context in which they might be realized is a context which is maybe related to what you were talking about, but I don't know.
Thanks.
So, okay, so maybe I'll skip ahead a little bit. I'll just mention one other thing because it's sort of interesting. In de Sitter, so here's an example of a Big Bang cosmology. So let's talk about de Sitter with spherical boundaries. Let's do d equals 2 and 4. You can do it for 3 + 1 dimensions too. It's a little thornier. Just the expression is less nice. So here is an example of Big Bang or Big Crunch cosmologies. We see that the warp factor goes to 0 size at t equals 0. And it's just, so in other words, you might ask if there are solutions to the gravitational path integral, which have the feature that you have a power law in time singularity at t equals 0 at the Big Bang, and then are asymptotically de Sitter. And there aren't any classical solutions of this form, even though these seem like natural boundary conditions for talking about cosmology. But nonetheless, there is a quantum, there are these constrained saddle solutions which satisfy these kinds of boundary conditions. And so there's something interesting to say about de Sitter here as well. And I can say more about that maybe during the discussion if people are curious what these things mean. But maybe, okay, so so we've showcased some non-perturbative effects in quantum gravity, some new ones, but we can ask, what is their physical significance? And maybe the cosmological solutions are suggestive, but what I'm going to do is do a complete non-perturbative analysis of the ADS3 Euclidean wormholes and show that they encode statistical properties of black hole microstates. So so let's see, I may have to skip through some of the details of this, but I'll hopefully get to the different punchlines.
Jordan,
So
you can also have like a little bit of overtime. So if you need like
I'll
5
try
more
not to
minutes
go,
or 10 more minutes.
I'll try not to go over by more than a few minutes.
Okay, sounds good.
Okay, so let's talk about the context of pure ADS3 gravity. So this is going to be a place where we can really put to work our constrained saddle solutions. And ADS3 is nice because it's a setting in which we can compute one loop determinants in the gravitational path integral explicitly. Whereas in higher dimensions, it's much more difficult and maybe not tractable. So the solution, so pure ADS3 gravity is classically a soluble theory. And it's a theory that has black holes and has gravitational edge modes. Namely, it doesn't have bulk gravitational waves, but it does have large diffeomorphisms or boundary gravitons. And which the interactions in the theory are marginal. And it contains a moduli and a sum over topologies. And in some senses, it is a good model of a nice toy model, perhaps, for quantum gravity in higher dimensions, or at least this is one of the motivations for studying it. Now, there is a funny feature, which I'm not going to get into so much here, which is that there is a spectral gap between the vacuum state and the BTZ threshold, namely the threshold in which there are black holes, BTZ black holes. And the spectrum above is continuous. So this is a strange feature to have. So if you were to ascribe to the usual ADS-CFT duality, in which you expect that a gravity theory like such as ADS3 would be dual to a compact unitary CFT. Well, if it was compact CFT, you would expect it to have a discrete spectrum, and it appears that pure ADS3 gravity does not have a discrete spectrum. So that's historically been viewed as some weird pathology, but maybe we'll see later that this is actually a feature instead of a bug. So here's the basic setup. What we want to compute is the amplitude. Let's call the complex structure tau1 and tau2 to conform to more standard notation. We're going to consider two torus boundaries with complex structures tau1 and tau2 respectively. And we want to consider the amplitude of the wormhole which connects them, the simplest wormhole which connects them. And as I mentioned before, this is a problem which has no smooth saddle points. So we use the technology of constrained saddles to allow us to compute this amplitude. So this is the amplitude, the torus times the interval with the complex structures tau1 and tau2 on the conformal boundaries. Great. So let's begin with Lorentzian signature. So it's going to be convenient for technical reasons to work in terms of first order variables instead of in terms of the metric. I can explain why in a moment. So we're going to do this. We're going to look at the constrained saddles in a first order formalism instead of a second order formalism.
Sorry, Jordan, just really quickly in the last slide, just to clarify. So you fix the topology and you integrate over all of the like boundary graviton loop corrections on top of that topology, or are you also allowing different bulk topologies?
No, we're going to fix the topology, but there's going to be moduli. And so we fix the things we're fixing are the topology and the complex structure of the boundary tori. And we integrate over everything else, including as you said, the large diffs and also whatever other moduli we have.
I see. Okay, so like just to compare with like Maloney-Witten, there you would sum over like the different possible ways to like pick cycles for the torus. Here you would just fix one of those.
Oh, well, there is an analog of that here, as we'll see.
Oh, there is. Okay.
Yeah. That's right. Yeah, I mean, there's going to be modular invariance in the final answer. Okay, so the reason why we're working in first order variables in terms of field binding to spin connection, which are PSL2R valued fields, is that it has the form of a phase space path integral, like from quantum, that we learn in quantum mechanics, the advantage of having, because there's terms that are like PI/QI dot, which is roughly like this term over here. But the reason why this is useful, I've also included the possibility of having constraints. The reason why this is useful is that in phase space path integrals, it's easy to read off what the path integral measure is, because it's just P wedge Q. And similarly in gravity, you can also, in the first order formalism, read off what the path integral measure is. It's just the Pfaffian of the symplectic form. So anyway, so at least in the gravity context, there are Lagrange multipliers in the gravity setting, which are the temporal components of the field binding the spin connection. And these will impose curvature and torsion-free constraints. If you're familiar with JT gravity, it's much like how the dilaton is imposing that you have metrics of constant curvature. So maybe, okay, so the idea is that we're going to integrate out the Lagrange multiplier fields and solve for the constraints that are compatible with our boundary conditions. And then we get residual fields phi bar on each boundary, which are going to correspond to the fluctuations of the boundary gravitons. So in the interest of time, since I don't want to go too much over, and I have some more things to tell you about, I may skip over some of the details of this analysis. But let me mention one thing. If we look at, okay, so we have done a constrained first approach in which we have integrated out these Lagrange multiplier fields, which impose these curvature and torsion-free constraints. And in doing so, we are left with the residual fields are all spatial. We've integrated out over this sort of one of the directions, which is like a Euclidean temporal direction. And here's an example of a geometry. So I've put it back into first order formalism for the spatial components of the metric that we are integrating over in the path integral once we've imposed the constraints. We see that here B, I've chosen constant B. This B parameter is related to the size of the bottleneck. That's the important thing which I wanted to mention in this slide. So there's a modulus which is related to the size of the bottleneck of these configurations. So, okay, so the full action for the boundary gravitons is sort of a mess. It's this complicated looking thing, but and there's also twist fields. Okay, but the way you should think about this is this is the higher dimensional analog of the Schwarzian action in Joukiev-Teitelbaum gravity. It's called an Alexeyev-Shadashvili type action, and it looks, in fact, a lot like having a few copies of the Schwarzian, but it's a higher dimensional version. So when the dust settles, maybe I'll skip ahead a bit. We can exactly, okay, so I'm going to skip ahead to the punchline. We do some techniques using using supersymmetric localization. And at the end of the day, this is the answer that we get for the, after slightly elaborate calculation, for the amplitude, where we have a sum over these SL2Z images, which is like related, which is kind of analogous to this Maloney-Witten computation. It's like a relative SL2 between the two boundary tori, and Z0 is the partition function of a compact boson. So this in and of itself is not a particularly enlightening answer, but I'm going to show you that it contains something which is totally kind of amazing. That it's encoding some physics, which is very surprising. So this is our final answer, and let's try to extract some physics from it. So let me just make a few remarks about some features of this answer, which is that the sum over the SL2Z images, these SL2Z images that are relative between the two boundary tori, it almost converges, but the divergence is a pure additive constant, which we can treat using zeta function regularization. And this function, this amplitude is double modular invariant. If we do independent modular transformations of the two tori, this renders the amplitude invariant. So what we're going to do is we're going to consider large, so we're going to take the imaginary part of tau 1, the imaginary part of tau 2, we're going to call it beta 1 and beta 2. We're going to consider the limit of beta 1 and beta 2 large with the ratio fixed. So this is going to be, at a moment, look like looking at low temperatures. So let's disentangle the answer a little bit. Okay, so I'll first say some words and then I'll show some equations to sort of, so we understand better what's going on. So we're going to basically look at the wormhole amplitude at fixed boundary angular momenta And we're going to separate it into a contribution from primary states alone and contributions from descendants. And so when we do this, and I'll say in a moment what this means physically, if we look at, so we have this wormhole amplitude, and we're going to look at sector, so how do I say, we're going to look at configurations of fixed angular momenta on the boundaries, which are S1 and S2, and we're going to just extract the contribution from primaries. This is the answer that we get, where E sub s is the threshold energy for a BTZ black hole at spin s. So let me say, what exactly does this mean, and what is it that we've actually extracted? So let me give this actually a more concrete interpretation of what we've been doing. So what have we computed? Well, I'm going to argue that we've computed a quantity which is like this. So let's just look at this quantity for a moment. Suppose that we have a Hamiltonian, which corresponds to the CFT, which is dual to ADS3 gravity, if such a Hamiltonian exists. And we're going to look at this. This is going to compute the torus partition function in a sector. So the Hamiltonian commutes with an angular momentum operator. So we're going to look at we're going to block diagonalize the Hamiltonian, look at the Hamiltonian in a sector of fixed angular momentum S1. So this is like looking at the Maloney-Witten partition function for inverse temperature beta 1 in a sector of fixed angular momentum. Okay, so suppose that we computed two of these. So this is like computing two copies of the Maloney-Witten partition function, or the way, that's one way of thinking about it, two copies of the torus partition function, where you have different inverse temperatures, and you're looking at two different blocks of the Hamiltonian in sectors of different, potentially different fixed angular momentum S1 and S2. And the question is, in gravity, what we are computing is not the product of two torus partition functions, but something like a connected contribution. We are filling out the two tori with a wormhole that connects them in between. And we are asking, what is this amplitude equal to? I mean, I'm trying to draw an analogy between, in a putative CFT calculation, what is the kind of quantity that this wormhole amplitude should be encoding? And I'm saying to you, it's as if you were computing a connected contribution to quantum gravity with two boundary tori, where you have fixed the angular momentum on the boundaries. And so you can ask, what would we expect if we had done a random matrix theory calculation, if instead of HS1 and HS2 belonging to a particular instantiation of a particular CFT, what if these were random matrix theories? Or what if we did this in random matrix theory where there's an ensemble of matrices, and if we consider a random matrix theory where we have a spectrum that looks like a density of states at fixed angular momenta that looks like the Maloney-Witten one, where we start at the BTZ threshold and then we trail off to infinity, then there's actually a universal answer in random matrix theory, which is this. So random matrix theory tells you that this is the answer that you would expect for this quantity if the density of states looks like the one that you would expect from ADS3 gravity, we get a certain dependence on the betas and the threshold energy. And the interesting thing about this is that if we compare this with the statistics of the primary states, we find that it exactly matches the random matrix theory prediction. So what this is telling us is that ADS3 gravity is telling us that the energy statistics of primary states, or rather the BTZ black holes corresponding to primary states, their energy level statistics exactly quantitatively match the prediction of random matrix theory. So these are independent calculations. This is a universal random matrix theory calculation. This is the output of the constrained saddle gravity computation. You can check you can check that these these are exactly equivalent. So furthermore, this quantity can also be computed by bootstrap techniques that I won't have time to tell you about. So the point is that ADS3 gravity, these wormholes, are encoding the energy level statistics of BTZ black holes. And furthermore, we see this kind of remarkable method of random matrix theory. And this is like a higher dimensional version, a 3D version of what happens in JT gravity. So let me make a few comments and then we'll go to a discussion section. I want to emphasize that this is an interesting answer, but it's a strange answer. So to see why it's strange, let me review a quick fact about this quantity called the spectral form factor. So this quantity has the feature that if we look at beta 1 and beta 2 as being complexified, we look at beta plus IT and beta minus IT, and we look at large T, we get what's called a ramp-like behavior. And so here what I've done is I've taken a random matrix ensemble called the Gaussian unitary ensemble, and I've computed this quantity in random matrix theory. And let's not worry about this behavior here. This ramp behavior, this linear behavior is this. This is called the ramp. And it actually goes on for a very long period of time because this is a log-log plot. It actually goes on for an amount of time, which goes like the Hilbert space dimension roughly. So notice that if I average this quantity over 10,000 instances of this random matrix ensemble, we get this purple curve, which is a smooth ramp. But if we compute it for a single Hamiltonian, we would get these very erratic fluctuations. So what's interesting is that we see a dichotomy, we see a juxtaposition between the quantity. So we have computed a quantity which in random matrix theory would be smooth, but if we had a single boundary CFT would be erratic. And what we have found is that ADS3 gravity is handing us a smooth ramp and not an erratic ramp. So this is telling us that ADS3 gravity, at least from the point of view of the gravitational path integral, looks like an ensemble instead of a single CFT in terms of its energy level statistics. So we can ask the question, is pure ADS3 gravity dual to an ensemble? And the short answer, in the interest of time, is that you could ask first, is it dual to a random matrix theory? And on the one hand, we've gotten this nice agreement with random matrix theory in this computation. And furthermore, the Maloney-Witten density of states, which is continuous, is actually maybe good in this setting because you expect to have a continuous density of states if you have an ensemble. But there's some reasons, maybe most notably the modular invariant of the amplitudes, which do not look like they belong to random matrix theory, leading to a conjecture that maybe pure ADS3 quantum gravity is not dual to an ensemble of random matrices, but an ensemble of conformal field theories. And this is a question which is under active investigation. So let me maybe conclude. So I'll go to a discussion. So let me just quickly say the summary from the beginning, just to summarize, and then I'll just have one last slide. So we've shown that there's a vast collection of new non-perturbative effects in the gravitational path integral in higher dimensions for different values of the cosmological constant. And some of these show us that ADS3 gravity encodes a generalization of random matrix theory, which provides compelling and quantitative evidence for a duality between ADS3 gravity and an ensemble description. And furthermore, I didn't have a chance to talk about this, but these amplitudes in ADS3 gravity can also be computed by a bootstrap technique. So ensemble gravity can actually be accessed by a generalization of the conformal bootstrap. So as a final discussion point, and instead of calling it ensemble gravity, let me maybe propose a slightly different term, which is mesoscopic quantum gravity. And let me maybe just show you final things on this slide, and we can, so maybe I'll just keep it here. I'll just leave this slide up, and thank you all very much for your attention.
Thank Jordan for the nice talk. Thank you, Jordan.
Thank you.
Thank you.
Maybe now we can do a few questions, things like that. I have a very quick question to you, Jordan, actually, given these final discussions. So what do you think is, I mean, it might be a super naive question, but in a sense, you could get away for looking at this random matrix theory for this property of ADS3, right? But yes, in the end, we expect that more generally, maybe this is an ensemble of CFTs. So how exactly could you get away sort of like at looking for ADS3 at looking at random matrix theory and not have to specifically look for CFTs just because of the observable you're looking at? Like it's not really sensitive to.
Sorry, well, so let me make a comment, which is that I didn't say this, but this computation that we did in ADS3 also looks like it works in higher dimensions. In other words, this thing where you get random matrix theory statistics of small black hole microstates above threshold also appears to be true, for example, in ADS5, like for a boundary that's S3 cross S1, which would be relevant for, ADS CFT in the examples we know and love. But the thing which is difficult about it, or the thing which is still thorny and under investigation, is computing the one loop determinant in gravity in higher than 3 dimensions is just really tricky, and how to do it the right way. So I do actually anticipate that the calculation that I shared with you in 3 dimensions actually probably does work in some appropriate way in higher dimensions, and also yields the random matrix theory statistics. Now, I want to distinguish, I think, related to your question about having random matrix theory statistics doesn't mean that you're dual to a random matrix theory ensemble. Yeah. That's sort of the key point, which is that you expect on general grounds that if you look at the level statistics of a chaotic Hamiltonian, they will, or a generic Hamiltonian in the appropriate sense, that it will exhibit random matrix theory statistics. But, and so in a certain sense, it's telling you that these constrained saddles in higher dimensional gravity know something about these random matrix theory statistics, and are giving you kind of a geometric instantiation of something that computes these random matrix theory statistics. But the thing which is weird about them is they are seeming to compute an ensemble averaged version of those random matrix theory statistics. And what the nature of that ensemble is, or how we are to interpret that result, is open to question for sure. But the point is that a lot of these ideas, these are providing sort of these concrete, calculational tools and examples of ensemble gravity in higher dimensions. And I didn't have a chance to talk about the de Sitter, but there is an interesting story about what ensemble gravity means in de Sitter in the context of these constrained saddles that I could say a bit about.
Thank you.
So I had a question. What is the H supposed to be for a generic CFT that you're computing trace e to the minus beta H of? Like, is it supposed to be like the dilatation generator or something like that?
Sure. I mean, just the Hamiltonian. I mean, yes. Or how do I say?
I may be making the wrong association here. I was kind of thinking of, for example, the ensemble of CFTs that Hartman and these people talk about in the U1 gravity example, where you really just have the conformal dimension and some OP coefficients. So there's no like Hamiltonian per se that you're just given. It's just some CFT defined by a space of OP coefficients and conformal dimensions. And I was kind of imagining the ADS3 case would be similar. Yeah.
Right. There is a Hamilton. I mean, they're looking at, how do I say? Let me just remember the details. I mean, they're looking at, they have an action. They have, they have moduli that they're averaging over. And I don't see the issue with having, I mean, they're considering a family of CFTs, which you can write down the action or the Hamiltonian,
Okay. Yeah, for some reason I was.
Isn't it a problem for CFTs that like any Hamiltonian would actually have a CFT that corresponds to that? That's why you sort of have to know all the moduli of things. Is this related to that? Or am I misinterpreting your question then?
Right, yeah, I was, my question was basically just because, like usually it's just hard to identify a Hamiltonian.
Exactly, with a CFT. Yeah.
Usually we talk about the like OP coefficients and the conformal dimension. But that may not be the case in this example. I was just
Sure. Yeah, it's not the case in that example, and but I'm imagining that there's some. I mean, in ADS CFT, we of course often imagine that. Okay, well, we talk about the boundary Hamiltonian, the Hamiltonian the boundary theory, and that is the sort of thing that I have in mind. I mean, but of course, I should say in this context, it's just a suggestive. Like, it doesn't really necessarily mean anything. It's just something to sort of have the right mental picture of what it should be computing.
Right. Oh, for sure.
But of course, in the context of these papers that you were just describing, well, it actually does. I mean, you can be very concrete about it. And I should also mention that some of the bootstrap techniques, by the way, that we developed that also provide an alternative computation of the wormhole amplitudes and the gravity case. If you give them if you do them a slightly different way, then you actually get the solutions of. I believe the people who computed. I believe that only in the Maloney-Witten paper did they compute the two-sided contribution, and you get the wormhole. I mean, you basically get the answer in that setting.
I see.
So there's a way of bootstrapping both things, the gravity and this sort of Chern-Simons-y thing. I mean, this
Okay.
abelian Chern-Simons.
Yeah, so just another minor question I had. With the computation that you were doing, so you sum over these SL2Z configurations, and in the case of Maloney-Witten, when you sum over the SL2Z configurations, they're like relating different saddles in the bulk. These like BTZ, like these like SL2Z black holes, basically. And in your case, is it somehow obvious that when you do an SL2Z transformation of a constrained saddle or constrained instanton, that it takes you to another saddle that's constrained, that solves the same constraint? Like it, so your parameter, you're basically summing over all the different possible constrained solutions, right? And you're relating them all through SL2Z transformations. Is that right?
Yeah, I mean, it's something that has to be demonstrated.
Okay, so it's not like I was just wondering if there was like an easy.
I mean, you would expect it to be true, but
yeah,
it has to be checked.
Okay.
I mean, the nice thing is, right, yeah. I mean, one other comment, maybe is slightly tangential, but that might be interesting, is one thing which is really nice about this computation is that of the wormhole is that, the Maloney-Witten computation has some famous pathologies, not just that it is continuous, but it also has some negativities. And there's been work recently, by Toriachi and Maxwell, in which they show that maybe there's other configurations you can include to get rid of these negativities and so on. But the thing which is nice is that somehow the that the wormhole thing is actually totally fine, is that it actually doesn't have any pathologies. And so in a certain sense, it's like better behaved, or it's more straightforward to compute it in its totality than the Maloney-Witten partition function, which might be missing things.
Right. Okay. I see. Also, I know you guys were particularly focused on the two boundary case.
Yeah.
But do you know like how much more difficult it would be to compute the like n boundary version of this?
So what I would expect, so a suggestion, I think that was due to Juan, was that maybe a natural guess as to what you do for three boundaries is that you would do a constraint on the sum of the sum of the pairwise distances between the boundaries or something like that. So the short answer is that I just don't know how to patch together. I just don't literally know how to solve the geometry problem in 3D, but maybe it's possible numerically, like you could have, find numerical solution if you set up the problem the right way. But my intuition is that they exist with both solutions of this kind with a larger number of boundaries and also with more interesting bulk topologies.
I see.
Like even in the two-sided case, you could ask what happens if you have more interesting bulk topology.
Right, like you have G.
Right.
Thanks.
So any more questions for Jordan?
One question. So you have managed to show that the random matrix theory and the two-point function in terms of wormholes matches at leading order. So is there some, should we expect its matches for higher orders as well?
Well, the thing which is universal in, so the thing which is universal in random matrix theory is so there's a few things to say. One thing you can ask is about what happens at higher topologies. So in other words, if we didn't just include the trivial topology of the torus times the interval, if we had something more interesting in the middle, what would those look like? And is there even anything like a genus expansion in 3D gravity? And as far as I know, there isn't, or there isn't something like that that's known. So it's a little confusing what what these things would look like, how they would be suppressed, and how that would all work. But at least as far as the leading contribution goes, which is just the leading topology, the torus times the interval, well, the answer is that near threshold, at the BTC threshold, it does agree with the random matrix theory answer. But there's interesting corrections that are suppressed in the temperature, because the temperature away from the threshold. Not the temperature. Sorry, they're literally just suppressed in beta 1, beta 2 is what I meant to say, and they're power law, and these are non-universal. But what I think they are is that you need them for the actual answer to be modular invariant. So it's sort of like a relic of the fact that you're doing something that looks like random matrix theory, but is also modular invariant. So in a certain sense, these corrections have to be there, but they're not something that belong to random matrix theory specifically, except for the leading order. The leading thing in the 1 over beta. Yeah.
Thanks.
So any more questions?
Sorry, I had one more question, but if someone else has, then they should ask first, because I don't want to.
Sure. I should also mention one other thing. Just I know that usually with these things, well, it's the nice thing about giving talks in person, of course, is that you can chat with everyone. But since, of course, we can't do that, feel free, of course, after the talk, if you have any questions that you want to ask or want to Zoom and chat about anything, feel free to email me, and I'd be happy to talk about anything. So
Yeah, and also next week, Jordan, we will have more chance to bother you.
Yes.
Yeah, to bug you more officially, but yeah, very good. Thank you.
I forgot. Yes.
Yes.
All right, yes. So go ahead. Yes.
Yeah. So in 2D gravity, so what SSS did was they just resummed the entire sum over genus to get the partition function. Is there some sense in which the constrained saddle can give you the you can use some kind of saddle point approximation to get the leading order contribution to the partition function?
Not for the 2 boundary one.
Not for the 2 boundary. Is there a reason for that?
Well, it's also true in you mean why it's also true in Sod-Schenker-Stanford?
No, so in their case, so in their case, it's just not a saddle at all. So I would, so you just can't do the saddle point approximation, but I'm wondering if there's some sort of approximate saddle point approximation that you can do if you have a constrained saddle. It's like a partition function where it's not, there's an additional boundary condition or something that you put in the path integral. So it's a slightly different.
But that, in a certain sense, what you're describing is what a constrained saddle is. It is a constraint that then reduces it to a standard saddle type problem on the constraint surface.
Right. So yeah. So I'm just wondering if it's is there a meaningful saddle point approximation in that for that kind of partition function?
That
in the G Newton expansion.
Oh, sure. Oh, I see what you're asking. So sorry. So let me maybe make a comment that this ADS3 computation, by the way, is exact. It's not. You can actually, just like in JT, you can actually do the full path integral. So, it has this one loop exactness properties, and there's various things that are going on, but the answer that I showed you is not an approximation of the thing, it's an exact thing. In higher dimensions, though, you would have to make them saddle approximations in the sense of constrained saddles. So you really do have to saddle in the directions that are not the constrained direction.
Oh, I see. Okay. I understand what you're saying. I was curious if one wanted, could they do a saddle point approximation of the constraint partition function?
In the constrained direction. Well, the question is the 2D example that I showed you before, or just 0 plus 0, but okay, 2 variables. You could say, could you do a saddle point in B?
Yeah.
And the answer is, well, would you put B at 0? I don't know of a systematic, I don't know of a way of doing that in every case.
Okay, I see.
But just related to that, there is a theory of, you can ask in finite dimensions, you know, is there a theory? We have a very good theory of, you know, steepest descent, stationary phase, you know, stuff about whatever. But is there a theory of these constrained saddles? And as far as I know, there's the people who study resurgence and Lefschetz thimbles and stuff, to some degree, really, the technology is there, but I'm not sure these have not been worked out and in this kinds of cases that are relevant here. And so something that I'm thinking about is just, what do you even do in finite dimensions? Like, because what you're asking is sort of related to, okay, is there something non-arbitrary? Is there not a non-arbitrary prescription for how to compute these constrained saddles, these valleys? If you have a valley, why do you integrate along the valley as opposed to look at some other point? And the thing that seems to be the case is that there is a non-arbitrary prescription about what you're supposed to do. There is something which gives you, in a certain sense, the best approximation. And in many cases, it is integrating along the entire valley.
I see. Okay. Cool. Thank you. Yeah, thanks for answering all the questions.
Sure. And then sorry again for going over. I apologize.
Very good. So assume if there's no more questions, so let's thank Jordan again. Thank you, Jordan.